Okay, we've already kind of gone through all of this before, but I'm just going to maybe re-talk about it. Common forces, normal, tension forces, real and fictitious forces. Oh, I'm interested to see what that means. Apply Newton's laws to solve stuff. Okay, normal force, just that whole thing, is the idea that if you're touching something, it won't let you go through it. So if I'm sitting on the floor, I can't go through the floor. If I'm, sitting on a ramp, I can't go through the ramp. If I am I don't know. I was going the wrong way. If I am a helium balloon, I can't go through the ceiling. Okay, this is the normal force preventing the helium balloon from going through the ceiling. Okay, makes sense? Normal force, and it's always normal to the surface. So if you ever draw a normal force without a perpendicular sign, you've done something wrong. Okay, and normal is it's called a reaction force, which means it only exists if you make it. So the ceiling by itself is not creating a force, but then when the balloon comes up to it, then there is the ceiling has a reaction to the balloon because the balloon touches the ceiling. It's that whole equal and opposite reaction thing. Okay, so that's where that comes from. But it's normal too. Okay, look at that. We know things. All right, and then here's something, I don't really know what they're trying to do here. Oh, yeah, okay, so if I'm holding a bag of dog food, here's my hand. I have a thumb. Thumb? I don't know what thumbs look like. Here's my hand. Here's a hand. And here's my bag of dog food. Okay, if I'm just sitting there doing nothing, if I draw a free body diagram of the bag of dog food, there is a weight of the dog food and then the normal force from my hand onto the dog food, I guess. That's a terrible example. Same thing as if it's sitting on the table. They look the same. The dog food doesn't care if it's sitting on my hand or sitting on the table. The free body diagrams, whoa, what just happened? The free body diagrams look the same. Okay. And don't do this, because normal force is not always equal to mass times gravity. It is only equal to mass times gravity in very, very specific situations, so stop memorizing equations and actually look at the picture and see what's going on. So never, ever, 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 ever just memorize equations. And I say this as someone who did nothing but memorize equations for years and then had to unlearn it, and it was so painful. Okay, this is a great example of a time when normal is not equal to mg. Okay, so we've got, this is your standard dude on a ramp. Okay, so I always struggle with science. By science, I mean geometry. So let's just pretend this is 30 degrees. All right, so gravity. Okay, if I'm going to draw a free body diagram, first, before I draw free body diagrams, let's look at geometry, because I know that gravity is going to go straight down. So there's going to be a straight down component of this. So I kind of would draw in stuff and be like, okay, so that's 90 because that's a straight downy thing. So then that makes this 60. So then what if I need this angle here? So that's 60. This is 90 because that might be a normal force, maybe. So then if that's 90, then this is 90. So this is 30. And then these are interior matchy angles. So this one's got to be 60. And then these are other kind of interior match. And if you're like, I already get this, well, good for you. You're smarter than me. Way to go. 30. Okay. Because usually half the time when I would get these wrong as an undergrad, it was because I had the angles in the wrong place. Okay. So if you can get here, you're in wonderful shape and you're amazing. And if not, just review geometry until you can get there. Okay. So the idea is if I have something on a chunk, 30-degree angle. Okay, now to make the math easier, believe it or not, I can pretend that my unit, or what do you call it, axes are different. So if I just start, let me kind of take a step back. So I'm going to take this and Can I just do something like that? No, it didn't do it. All right. Okay, so I'm going to draw this lighter. So we're going to, because this is really background. Okay. Because what we really want to do is draw a free body diagram of our, weight or whatever. Okay. So the box has a weight right now, and for sure it has a normal force, because that's all I'm talking about right now. And the normal force is perpendicular to the surface. It's not up and down. It is perpendicular to the surface that is happening. So in this case, this is the surface, is that little rampy thing. So that's where the right angle goes. That's why I was drawing this picture over here, is so that we made sure we could find where all these angles were. Okay. Now, what's going on in this original picture? Is there a frictional force? Okay. So this dude has impending motion, or is moving down, even though apparently we haven't talked about friction yet in this book. He's moving down the ramp, and there's friction, so there's friction going this way. Okay? So, I have two choices here. I can either make everything XY like this, or I can make everything XY like this. And you're like, but gravity always points down. No, I already got that. I got the weight. The weight is the gravity. Everything else now I can just do with math, which is bizarre. But remember, we said that X and Y motion is independent, but we only said that's because they're in perpendicular directions. It has nothing to do with the fact that I arbitrarily assigned this direction is X and this direction is Y. If this direction is X and this is Y, those two motions are still independent. Okay, as long as the directions are perpendicular to each other, they're still independent, so it doesn't matter which X and Y's I pick, as long as, well, it follows the right-hand rule, I guess, but that's just to keep the math consistent, but that they are perpendicular to each other. So for the purposes of math, I would much rather, instead of breaking these F and N's into two components each, I would rather just break the W. So basically the idea is that I could either break F into F and N into N and N to make everything lefty, righty, uppy, downy, or I could just break W into, or the weight into chonky, donkey, I don't know what that meant, and then I can just, I literally just moved my computer sideways like you could tell what I was doing, and then like in line with this, if that makes sense. Okay, so if I look at this picture over here, what was that angle? That angle right here was 30 degrees. So this angle right here is the same thing as this angle right here. So that's 30 degrees. Okay, so I've got 30 degrees here. Okay, and let's see. So the opposite component is sine. And this is why we don't memorize sine is y's or x's or whatever. We just memorize, or we learn that sine means opposite. So opposite is W sine 30. And if I'm really awesome, I know that that means 1/2 W, but I'm just not going to do that because I don't want to scare you right now. And then the cosine is the adjacent to the 30. So this is W cosine 30 degrees. Okay. So now if I'm doing the sum of the forces in the Y, and the X, remembering, now X is along the ramp, so this is X, positive X direction. So if I'm summing the forces, there we go. If I sum the forces in the X direction, the friction is going against me. Yeah. And then, I was looking at that, that seems weird. And the only other thing that's going, so, okay, an important to note is now that I've resolved those into those two components, I can basically be like, now this doesn't exist anymore because I've replaced it with those two others. Okay, so I have friction going up the ramp, and then I have negative W sine 30 going down the ramp, and that's going to be mass times the acceleration of the object down the ramp. Now, in a minute, since I know that the motion is pending downward, this number will be negative. Does that make sense? So the number itself will be negative because I'm accelerating down the ramp thingy. So the number will turn out to be negative. Okay, now some of the forces in the y direction. Okay, so I have n going up, and I have cosine 30, I can't spell, going down, and that equals the mass of the object times the acceleration in the y direction. Now, this is where it's a little weird. The way I've defined y, right? Y is this way. Uppy downy y is this way. It is not moving uppy downy this way. And if you don't believe me, turn your paper, rotate your paper 30 degrees, and then convince yourself. But it is not changing position in that direction. It is only changing position, like if I rotate my paper, it is not changing position in the uppy downy direction. It is only changing position in the lefty righty way. So in fact, the acceleration in the y direction is 0. So in this case, the normal force is the weight times cosine of 30 degrees. Not mg. I mean, the weight is mg, but now Newton's normal force is mg cosine 30 degrees. This is a super big deal because eventually, when we officially learn friction, which I think is maybe the next section or eventually, to get friction, you multiply stuff by the normal force, and the normal force is not always mg. So I cannot emphasize enough to don't memorize equations, but understand what's actually happening in the picture, look at what's going on, draw pictures, walk yourself through the math. Okay, let me see if there's anything else we really need to look at. So yeah, don't memorize this stuff, because that's exactly what I would have done. Does it tell us some kind of something? Does it actually give us a problem? Oh, her mass is that, and friction is negligible. What is her mass acceleration is? Friction, okay, yeah, so that's fine. You can read through that and work through it. So there's the mg cosine theta, but again, we're not memorizing this. We're just going to do the math and figure it out. Okay, second part of this is tension. Same thing. It's like tension is this. No, it's not. It's not always that. It just really depends on what's going on in the stupid picture. Please, 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 because, for example, if I have a box and there's tension going up on the box and the weight on the box. Okay, if the box is still, so like if it, or constant velocity, acceleration is 0, then the sum of the forces in the y, the tension going up minus the weight going down equals mass times acceleration in the y direction, but we know the acceleration is 0, so yes, the tension equals the weight. However, and this is where I get so angry at stuff and equations, because that's why. So if the box is moving, then the sum of the forces in the y is tension up minus weight down equals mass times some non-zero. So like if it was, I don't know, going down at, 100 meters per second squared or something like that, then the tension is not equal to the weight. The tension is equal to 100 m plus w. So, and that makes sense, right? Because if the box is accelerating down, the rope's going to be under a whole lot more tension, right? Than if it's just doing its thing. I feel like I said that right. Well, sorry, the other direction, I have it accelerating up. Yes, if it's accelerating up, if you're trying to pull the box up, you've got to like pull it extra, extra, extra hard to get it to come up to make up for the fact that there's a weight down there. So all of this to say, this is why I should never be in charge of teaching anybody anything. This is not always true, and this is not always true. And sometimes whenever you actually do these pulley problems, you define the positive direction is down, and we're not even going to get there yet. So worry less about memorizing the stupid equation to get through this assignment and more about what's actually going on, because that's going to serve you better, and you'll actually do better on homeworks and stuff like that because you'll know what's going on, and whenever they throw you a trick problem, you'll be like, this isn't a trick problem, it's just the same problem. Okay, so what is the tension in a tightrope? So we do, and something that is important is whenever we draw a rope, we do always draw tension going out. So, so if we have a weight here, we do always draw tension going away. And that's because a variety of reasons, but like basically if we drew the arrows going this way, it would mean that they were in compression, and we don't really use tight ropes in compression. That would be the opposite of a tightrope. That would be a fall on your face rope. So so that's a kind of an important aspect there is, thank you, that's, why are you there? Go away. So we do always draw the tensions going out away from the object because it is in tension. Another thing that we do assume is we do assume that if it's on a rope, that the tension in both of the ropes is the same. So that's a thing. So tension and tension the same, unless once you put a knot in the rope, now you have a certain tension in this rope and you have another tension in that rope. I drew them at different angles. They don't have to be at different angles. Even if they're at the same angle, if you put a knot in the rope, now you've allowed those two ropes to behave like two separate ropes. Does that kind of make sense? So like if I have a, like kind of your standard is like, oh, I have a light suspended by two ropes. So T1 and T2, and then I have a weight, and so you find out what the weights and the tensions are, and usually these are two different angles or something like that. But you would draw your free body diagram of like, okay, these are two tensions, they're pointing out, I need the sum of the forces in the x and the y directions to stay constant. Great. Whereas if you have like a tightrope walker on one rope and he's standing there, then you have the weight of the tightrope walker, and then since this is the same rope, the two tensions are the same, I guess. So one of my students loved the word inextensible. We assume the ropes are inextensible, meaning they don't stretch. They're non-stretchy ropes. If you want to do non-stretchy ropes, take classes like Mechanics of Materials, and then you can play with the stretchy rope game. Let's see. I feel like I'm going to solve a lot more of these problems later. Okay. Holy mackerel. Okay, there's more. I'm going to come back to this because I'm already emotionally exhausted from this video and I don't want to do anymore. And you're probably tired too. So there's going to be more on friction and tension and springs. And we haven't even actually started solving problems yet. So this will be great.